Hi everyone. So I wanted to make a video covering chapters 12.1 and 12.2, which cover the beginning of three-dimensional coordinate systems. And these aren't very complicated chapters, but they introduce some vocabulary and some notation that's going to be important as we move into the study of the calculus of vectors. So the first thing that we should point out is what exactly is we're studying here, and that's 3D coordinate systems. And all I mean by a 3D coordinate system is a real line and another real line and another real line, which is just fancy mathematical notation for points that have the form x, y, z. That's three-dimensional space. So what we're going to be starting with is what sort of objects are created when we set up equations involving more than one variable in this setting. Actually, one or more variables in this setting. So I guess the first thing we should talk about is what if I can find my mouse cursor here. Hello? Where the fuck is my cursor? So the first thing we should talk about is what a surface is. So in 2 dimensions, the usual object of study are graphs of functions. So if you write something down like y is equal to x squared, what you really mean by the graph of y equals x squared is the set of points that satisfy that equation. So it's all points x and y with y is equal to x squared. So the graph that you get out of that looks like this. Because every point on this graph is a point that you can plug into this equation and it satisfies it. Likewise, in 3 dimensions, we're going to have surfaces, which are sort of the equivalent of graphs in 2 dimensions. So in 3D, a surface is a sort of 2-dimensional object in R3, that is in 3-dimensional space. And the idea here is that if you look at it, it kind of looks flat. A line is 1 dimension smaller than the 2-dimensional space that it lives in. A surface is 1 dimension smaller than the 3-dimensional space that it lives in. So what do I mean precisely? Well, in 2D, an equation like x squared plus y squared equals 1 means that you're looking for points x comma y that satisfy this equation. I want x and y so that this equation is satisfied, and the set of points that satisfy that equation is a circle. In 3 dimensions, the same equation, if I have x squared plus y squared is equal to 1, now I'm looking for points x, y, z that satisfy that equation. And notice that the z doesn't actually matter. What determines whether or not the equation is satisfied is what the x and the y coordinates are. So what that means is we're not just going to get a single circle, let's say z is equal to 0, but we're going to get a circle for every single possible value of z, and the points, the coordinates of the x and y positions of the point will satisfy that equation anyway, regardless of the z value. So what you end up with is, in a 3-dimensional coordinate system, you end up with a circle at z is equal to 0, but you also end up with a circle at z equals 1, and 2, and 3, and 4, and so on. And so the shape that ends up defining the set of points that solves the equation is a cylinder. Because every point on here, for any value of z, will solve this. So for example, a really easy one would be something like 0, 1, 1, or 0, 1, 10. That also satisfies it because the 10 doesn't matter. The z coordinate doesn't interact with the equation that's used to define the surface. So this sort of object right here is called a surface. And the basic idea of a surface, like I said, is that it's sort of 2-dimensional. It looks flat. It doesn't fill up space. It just sits in space as a flat sheet. So the basics of geometry in this sort of setting are things like the distance formula. So you already know that the distance between points in R2, say xy, x1, y1, and x2, y2, d is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. The same distance formula holds in 3 dimensions, you just have to add another coordinate. So the distance between x1, y1, z1 and x2, y2, z2 is d equals x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. So you just go one more. Now with a notion of distance, you start getting a notion of things like regular sort of surfaces that can appear with respect to that distance. So the very first thing we can do with a distance is define the notion of a sphere. In 2 dimensions, we have circles. Circle is a set of points that are equidistant from some center, and that turns out to be an equation that looks like x squared plus y squared is equal to r squared. In 3 dimensions, we have spheres. A sphere is a set of points that is equidistant from a center, and so the basic equation is x squared plus y squared plus z squared is equal to r squared. That is, if you satisfy this equation, then the distance will always be the same for every one of these points from the center. You can shift the center of a circle with this equation. So this is centered at h comma k. And likewise, a sphere can also be shifted to have a different center. So x minus h squared plus y minus k squared plus z minus l squared is equal to r squared. And this is also a sphere, but now the center is at h, k, l. Okay, so this is sort of basics of 12.1. Essentially in 12.1 you're asked to deal with questions about how far points away from each other, the distance between points, identifying certain structures as isosceles triangles, say in 3 dimensions, and basic ideas of the sorts of surfaces that arise from very simple equations. So the last thing we'll mention here is an example. You could ask yourself, what is the surface defined by, say, z is equal to 1. So to satisfy that equation, we can pick any x and y value that we want as long as the z value is equal to 1. If you think for a second about what that means, if you have an x-axis and a y-axis and a z-axis, if x and y can be anything we want, but the z always has to be 1, then what we're looking at is actually a plane. And the equation of the plane is going to be given by, I mean, this is the equation of the plane, but every point inside here is going to have the property that it has coordinates that look like x, comma, y, comma, 1. The reason it's 2-dimensional is because we have 2 degrees of freedom. We can move in x, we can move in y, but the z value is locked into 1. So this is a plane that is parallel to the xy plane with z coordinate always equal to 1. All right, so those are the basics. That's 12.1. Not very complicated mathematics, but it's at least a place to get started here and do some exercises associated with this. These are not hard, but just get your feet wet with 3D coordinate systems. And next we'll talk about chapter 12.2, which is about vectors, vector notation, and similar ideas with distance and maybe even angle, though we're going to need the dot product to define that. All right, see you soon.